Introduction to High Brightness Light Emitting Diodes and Color Science. Welcome to this Introduction to High Brightness Light Emitting Diodes, HB LEDs, and Color Science training. This online training will introduce the basics behind color science, the industry terminology used when describing colors, the basic operation of LEDs, and how HB LEDs are used. All light is electromagnetic radiation that is visible to the human eye. How do our eyes perceive light? Within your eye's cornea are cells that react chemically to light. These cells are divided into rods and cones. Rods contain chemicals that react to the amount of light hitting each cell. Cones contain chemicals called color pigments that have different spectral sensitivities. Humans typically have three types of cones. There are short wavelength, middle wavelength, and long wavelength cones that react to specific color wavelengths. Since light is a form of radiation, it can be measured by wavelengths. Wavelengths between 400 nanometers and 700 nanometers are visible to the naked eye. Energy below 400 nanometers is considered ultraviolet, while energy above 700 nanometers is infrared. The three types of cones in the cornea have peak absorption rates for these particular wavelengths. The most common form of color blindness in humans is deuteranomaly, most commonly referred to as red-green color blindness. This is usually caused by the middle wavelength cones being shifted towards the red end of the spectrum. This makes it harder to distinguish between red and green shades. But looking at this color spectrum, you might be asking yourself, where are pink and brown and other colors that we can't perceive? Just as our cornea is divided into rods and cones, everything we see can be separated into a brightness component and a color component. The terms usually used are luminance and chrominance, respectively. Luminance is a pure measure of brightness alone, whereas chrominance is the dominant wavelength perceived. Another way to think of it is that the colors white and gray have the same chromaticity, but different luminance levels. It is the same with colors like pink and brown. Pink is simply a brighter shade of red, while brown is a darker shade of red. In the 1920s, two independent scientists decided to study human sight and how the human eye perceives color. In 1931, a group called the International Commission on Illumination used both scientists' research to standardize the measurement of color, and colorimetry was born. Colorimetry is the science that describes colors using numbers. The Commission decided to represent all visible light using three numbers, called Tristimulus Values. By using these three numerals, any color can be replicated exactly. The three numbers, represented by a capital X, Y, and Z, represent both the luminance and chrominance portions of everything we see. More specifically, Y is the luminance, X and Z are a function of the luminance and chrominance. One of the challenges faced by the committee was that they needed to provide some scalable method of representing chrominance. They decided on using a two-dimensional map of chromaticity that is now known as the CIE 1931 color space, or CIE XYZ color space. This is the CIE 1931 color space chromaticity diagram. It covers the range of colors that the average human can perceive. While colors exist beyond the curved figure, which other animals like insects can perceive, this curved figure contains the range of human vision, also called the gamut of human vision. The outer curved boundary is called the spectral locus, and the numbers in blue labeled around the curve are the wavelengths in nanometers of the colors. Each given color point within the diagram can then be represented as an X and Y coordinate in this diagram. For example, this specific point in the diagram has an x-coordinate of 0.2, a y-coordinate of 0.4. Pure white is represented in this diagram at exactly 1 over 3, 1 over 3. This is sometimes called the white point. An interesting property of the chromaticity diagram is that if I draw a straight line between any two points within the diagram, the color at any point along that line can be created using a mixture of those 2 points. Midpoint between these 2 colors would be created using an equal mixture of the 2 colors. So what is the connection between the chromaticity coordinates and the XYZ tristimulus values? As mentioned before, y is the luminance factor. The x and y coordinates are a function of the XYZ values as seen in these equations. So if we know y and we know the chromaticity coordinates, using the equations above, we can calculate x and z using these permeations. One integral use of color is in basic architectural lighting. One of the most important inventions in the history of mankind was the invention of electrically powered light. Thomas Edison first publicly demonstrated the incandescent light bulb on December 31, 1870. The downside of the incandescent light bulb is that the filament, which drives the light emission, burns away rather quickly. Average lifespan of an incandescent light bulb is between 750 and 1,000 hours. 23 years after Edison's demonstration, Nikola Tesla displayed fluorescent lights at the Chicago World's Fair. Fluorescent lights can operate 10 to 20 times longer than incandescent light bulbs. After those 2 demonstrations, there were very few major developments in lighting for almost a century. One rather recent innovation to the fluorescent light was the creation of compact fluorescent light bulbs in the 1980s. These incandescent light bulb replacements are both more energy efficient as well as longer lasting. The downside is that fluorescent lights contain trace amounts of mercury that cannot be disposed of traditionally. But what does the future of lighting look like? More and more light-emitting diodes, or LEDs, are becoming a popular choice for architectural lighting applications. This is because they are even more energy efficient and longer lasting than both fluorescent and incandescent lights. In addition, LEDs are completely green solutions. This is a picture of an LED light bulb. Clusters of LEDs can be packaged together to replace standard light bulbs. But besides just architectural lighting, LEDs can be used for a number of applications. LEDs can be used for signs, signals, flashlights, and more. Why are LEDs becoming more popular every day? LEDs have many advantages over traditional lighting sources. First and most importantly, it's extremely energy efficient. It produces more light per watt than incandescent bulbs. As the cost of energy continues to rise, system designers are looking for ways to be more energy efficient. Second, the life of an LED is approximately 100,000 hours, which is twice as long as the best fluorescent bulbs and 20 times longer than any incandescent bulbs. That means lights do not have to be replaced quite as often. LEDs do not need the use of color filters, which can mean a lower total system cost. Along the same lines, LEDs come in 16.7 million color variants, making it incredibly flexible for any design. This is especially important in large general signage applications. Unlike incandescent light bulbs that tend to turn yellow when dimmed, LEDs won't change color. LEDs can be designed to focus its light and do not require external reflectors. LEDs are durable. As the LEDs are encased inside a solid plastic case, there are no fragile glass and filament pieces. And LEDs can achieve full brightness in a matter of microseconds, which is important in dynamic applications. However, LEDs also have a few disadvantages. Because they are relatively new to commercial usage, LEDs are currently more expensive in lumens per dollar than incandescent and fluorescent lights. But even though LEDs are currently more expensive to purchase, they provide the long life and power savings that many systems desire. And as the LED market entrenches itself in commercial applications, the cost will eventually go down. Another relative disadvantage is that the LED technology is much newer than incandescent and fluorescent lighting solutions. As such, there are different design challenges that are being faced. For example, LEDs are more versatile and can create all different colors, but the exact color output is dependent on a stable current and ambient temperature. Because they are new to commercial use, many LED suppliers have very different methods for binning or labeling LEDs. However, new design challenges are usually resolved with new solutions that address those challenges. As LED-driven applications proliferate, so will the technology that implements them. So what exactly is an LED? LED stands for light-emitting diode. It is a semiconductor chip encased in a solid plastic lens that emits light. Color emitted from the LED depends on the composition and condition of the semiconductor material used for the making of the LED. The colors emitted can range from infrared to visible light to near ultraviolet. So how does an LED work? If we look at a single LED, it consists of the anode and cathode, which are the positive and negative terminals, the actual heart of the LED, which is the diode, and all of this is packaged together in a plastic casing. As we have mentioned earlier, light or photons are really forms of visible energy. In 1961, researchers at Texas Instruments discovered that gallium arsenide diodes generated infrared light when an electric current was applied. The energy generated was due to the reaction of the diode. So why does a diode emit energy? As we said, the heart of an LED is the diode, which comprises a section of N-type and a section of P-type semiconductor material bonded together. N-type material has extra negatively charged particles called electrons, while the P-type material has extra positively charged particles called holes. When the N-type and P-type material are combined with no external charge, the free electrons in the N-type material move from the negatively charged area to the positively charged area, P-type, and the free electrons move from hole to hole. As electrons from the N-type material fill holes from the P-type material along the junction between the layers, they form a depletion region. In the depletion zone, the material becomes an insulator and there is no current flow. When a voltage source, like a battery, is added, positive charge is applied to the P-type material and negative charge is applied to the N-type material. This external charge repels the holes and electrons at each end and draws them towards the other charge. As the electrons move away from the negative charge, they are expelled from the holes within the depletion region. When the free electrons are moving, current is able to flow through the diode. As this diagram shows, the diode can only carry current when the charge is in the right direction. If we were to flip our battery around in this diagram, no current would flow. If anything, the depletion region would increase. So how does an activated diode produce light? When the electrons move as a result of the diode being forward biased, they must drop from a higher orbital around the nucleus of the atom to a lower orbital. To do so, the atom must release energy in the form of photons. All diodes release photons, but not all are efficient enough to release light. In metals, there is no band gap between conduction band and valence band, so no visible light is emitted. For semiconductor materials, the band gap is larger, but varies depending on the materials used, and in turn, this determines the color of the emitted light. Here are some common semiconductor materials used to produce different colored LEDs. The most common LEDs are made of aluminum gallium indium phosphide, which creates high brightness orange-red, orange, yellow, and green LEDs, and indium gallium nitride, which creates blue-green and blue LEDs. Because different colored LEDs are made of different materials, they all have different trip points too when the LED turns on. A typical red LED may require a 1.7 volt at 20 milliamps, while a blue LED will require a 3.6 volts at 20 milliamps. The brightness of each LED will waver if the current flowing into the LED wavers. For this reason, the drive circuitry for LEDs must be controllable and stable. This is the electrical symbol for an LED. A simple LED circuit contains a voltage source and a tuned resistor. The value of the resistor affects the current flowing into the diode. However, one of the key advantages of LEDs is its long lifetime. That's only true, though, when the LED is operated within the manufacturer's recommended current rating. Delivering proper power to an LED system is crucial to maintaining correct light levels and life expectancy of the LEDs. Therefore, more complex drive circuits are typically used. The difference between standard LEDs and this new class of high brightness LEDs is the intensity of the light that can be produced. Light intensity, or luminosity, can be measured in candelas and lumens. The output of a single candle is approximately 1 candela, which is equivalent to 12.57 lumens. A standard LED generates as much light as 1 to 3 candles. A single high brightness LED, though, can generate as much light as 4 or more candles. In general, the brighter the LED, the more current it takes. As such, the brighter categories of LEDs also typically correspond to higher currents. However, we must be careful when describing high brightness versus high power LEDs, as they are sometimes confused. Technically, high power LEDs are LEDs that take over 1 watt to operate. High brightness LEDs are categorized by the intensity of light. In other words, a high power LED is typically a subset of high brightness LEDs as they generate over 50 lumens of light. But a high brightness LED is not necessarily a high power LED, as it can take less than a watt to power. The challenge is that both terms are used interchangeably in the industry. HB LEDs are used in many different applications. Looking at this chart, you can see that general signage applications are going to almost triple over the next few years. LEDs are quickly replacing regular light bulbs in large banners that can be seen everywhere from Times Square to sports arenas. In the past, these large displays were made out of several hundred individual light bulbs, each one using a separate color filter to get just the right shade of color. However, using regular light bulbs has many limitations. For example, as we have seen, regular light bulbs are power hungry and have very limited lifespans. Not only is it difficult to replace a light bulb in a 30-foot banner, it becomes costly as well. To maximize the advertisement's appeal, it's also better to be able to implement moving and changing images in the same space. Using fixed light bulbs with fixed color filters means only a single display can be generated. HB LEDs, on the other hand, can supplant the traditional light bulb in these applications while also providing lower power, lower system costs, longer lifespans, and more design flexibility. The challenge then becomes using the LED technology that exists today to create all the different colors needed to produce these banners. Remember the chromaticity diagram introduced in the previous slide? Imagine that your company wants to create a banner with your company logo on it using HB LEDs. Your company logo is probably made of certain colors that have to be accurate. Can you imagine a Coca-Cola sign with the wrong shade of red? Let's say the colors needed to be displayed cover these areas in the diagram. It will need these specific shades of green, blue, and red. Remember from the previous slide the interesting property regarding the chromaticity diagram, where all the colors along the line between 2 points in the diagram can be created from a mixture of those 2 color points. Well, if we have three LEDs, a red LED, blue LED, and green LED, then all the colors within this triangle can be mixed to create all the colors required by our company. But what if the sign also needed this shade of yellow? How could we compensate for the added requirement, since it lies outside the gamut of our three LEDs? Well, we can add another yellow-green LED so that the yellow now fits within the gamut. By mixing 3 or 4 HB LEDs together, we can produce a wide range of colors. The act of combining individually colored LEDs to create a spectrum of colors is called color mixing. The technical challenge with color mixing is that individual LEDs need to be tuned to get the right amount of each component. By adjusting the dimming of a certain color in the LED cluster, a completely new color is created. Dimming can be implemented in the LED drive circuit with the addition of a pulse width modulator, PWM, which varies the duty cycle of the current flow. The lower the duty cycle, the more dim an LED appears to be. Another way to think of it is when an LED is on full brightness, there is a DC current flowing through the diode. However, if the LED is half on, that means the forward current is operating at a 50% duty cycle. So even though there are many benefits for using high brightness LEDs and signs, there are a few design challenges that must be overcome. This concludes the Introduction to High Brightness LEDs and Color Science course. To recap some of the main points from this course, colorimetry is the science of representing colors as numerical values. The Tristimulus values X, Y, and Z are a representation of a color's luminance and chromaticity. The CIE 1931 chromaticity diagram is a two-dimensional representation of all the colors visible to the average human. LEDs are simply diodes encased in plastic that emit photons. Different materials used to create different diodes emit different colors. High brightness LEDs are simply LEDs that can produce more luminance. High brightness LEDs are quickly replacing incandescent, fluorescent, and halogen lights in applications ranging from architectural lighting, general signage applications, and LCD backlights.